Hello, everyone. Welcome back. Our keynote speaker today is Dr. Sara Seager, an astrophysicist and professor of physics and planetary science here at MIT. Her science research focuses on theory, computation, and data analysis of exoplanets. Before joining MIT in 2007, Professor Seager spent 4 years on the senior research staff at the Carnegie Institute of Washington, preceded by 3 years at the Institute for Advanced Study in Princeton, New Jersey. Her PhD is from Harvard University. Professor Seager is on the advisory board for planetary resources. She is also a 2013 MacArthur Fellow, the 2012 recipient of the Raymond and Beverly Sackler Prize in the Physical Sciences, and the 2007 recipient of the American Astronomical Society's Helen B. Warner Prize. She has been recognized in the media also, most recently in Time Magazine's 25 Most Influential in Space in 2012. Please join me in welcoming Dr. Sara Seager, who will speak to us about the search for Earth 2.0 and share with us some of her recent investigations.
Good afternoon, everyone, and welcome participants and families. I'm a professor here at MIT, and my job actually is to search for another Earth. And that's what I'm going to talk to you about, is how we're going to find Earth 2.0. So how many of you have been to a dark sky and seen the Milky Way? I really hope that those of you who haven't, if I could offer any homework to the parents here, take your girls out to a dark sky where they can see so many stars. I'll never forget the first time I saw that. My dad took me on a camping trip. It was his first and last camping trip, but I remember seeing the stars, and there were just so many of them. I just couldn't believe how many were out there. And now when I go out to look at the stars, I actually wonder, are there other planets? Are there planets around those other stars with people on those planets, or intelligent beings wondering the same thing about our star? Now, every star in the sky is a sun, and if our sun has planets, Mercury, Venus, Earth, Mars, etc., surely these other stars should have planets also, and they do. We actually know about thousands of planets orbiting stars other than the sun, and we call these exoplanets. Now, what we're doing is we're trying to find small planets that might be like Earth, ones where we can search for signs of life on them by way of gases in the atmosphere that don't belong. So we're not here thinking about little green people, waving at us or sending us a radio message, although we also hope that happens someday. We're just going to find planets and try to see what's in their atmosphere. Now, to start with, I wanted to show you a photograph of a galaxy, a collection of bound stars. We think that our Milky Way galaxy looks like this if we could look at it from above. And in our galaxy, there are hundreds of billions of stars. Now, our universe has over hundreds of billions of galaxies. So if every star were to have an Earth, how many Earths would be out there? You can just do the math. And the great thing is you really could do the math. And I know this would be a really easy problem for you, but believe it or not, for most of the general public, they actually can't multiply those two very large numbers together. So 100 billion times 100 billion, you can have 1 followed by how many zeros? I think it's 22 zeros. It's a lot of stars out there. The only ones we can search are nearby, and I'm going to start here by showing you this little movie clip of what our galaxy would look like. But as it zooms into where our sun is, it's actually a real map of the sky. All those little points, I'm going to pause and see if you can see them. Aha, okay, it's a little hard to see, but see all the little tiny points here? I don't know if you can see them from back there. The highlighted ones that are colored yellow or red, those are stars with known planets. All the other ones are real stars in the sky. It's a real map of the sky. And what this movie is supposed to do, this little animation, is help you see just how many are out there. And this animation zooms in on our solar system towards our own sun and Earth. And it's actually going to take us to Earth, to the west coast of North America. And if we could look at the night sky in the spring, these are the stars that we'd see. Actually, we'd need a telescope or binoculars to see all of the stars shown here. But this is actually a real map of the night sky with here the constellations are overlaid. And this software here, it's called NASA Eyes on Exoplanets. You can actually download the software. I had nothing to do with creating it. I just love showing it. And you can click on the stars and see what kind of planets are there. But this particular movie clip from it is just so I can go through it relatively quickly. There's a special patch of the sky. Does anyone know what this is? You don't have to answer, but I'm wondering, there must be at least one person in the audience who knows what this is. This patch of sky actually is where a special telescope called the Kepler Space Telescope looked at the sky for 4 whole years. I'll come back and talk about that in a moment. But here we can also search for one, and here it typed in Kepler 186, and this software will take you to that system. And look, Kepler 186 is a small star with 5 planets orbiting it. And actually, one of these planets is in the so-called Goldilocks zone. It's a distance from its star where it's not too hot, not too cold, but just right for water, just right for life at the surface of that planet. Assuming that that planet has a thin atmosphere like Earth's does. And in this particular software, too, it's zooming in really close. And this is where the fine print says, hypothetical visualization of planet. Because we don't have any real photos of planets orbiting stars far away like this. They're just simply too far away. So that's that introductory movie. And I want you to know that I make models of planets using physics and applied math and big computer programs that I or my students or research group write. And we interpret data from the Hubble Space Telescope and other telescopes. But it would be too complicated to walk you through all the models, although I do have some math to show you later on. So instead of that, I'm just going to show you a few illustrations of planets and what we speculate about these other planets. And we actually have some of these posters. This one is a travel poster. It's this retro kind of thing that they used to have posters back even before my time when they tried to encourage people to travel to other places. So this one says Kepler 186f, where the grass is always redder on the other side. And here you see there's 2 astronauts on this other planet looking at those red trees. And the reason this little speculation came about is the star itself is red star. It's not a yellow star like our sun. It's a small red star. And people imagine if it's giving off its maximum amount of energy at a different wavelength than our sun, perhaps the vegetation also looks different. Experience the gravity of HG 40307G, a super-Earth. And this particular planet, it has a gravity of about 1.5 times Earth's surface gravity. And so it's just showing you could go there, and we're imagining that just for fun, someone could travel to these. They're too far away for us to go to, but you could travel there and parachute down. Relax on Kepler 16b, where your shadow always has company, the land of 2 suns. And actually, there are planets that orbit 2 stars. And so on this particular planet, you would always have 2 stars in the sky, 2 suns in the sky, and you'd always see 2 sunsets. So science fiction got some things right. One of my favorite planets, this is Tatooine from Star Wars, in case anyone didn't notice. So one of my favorite planets, and this is my last picture of planets, is this artist's conception of Kepler 10b. What we found in exoplanets was we haven't found any solar system copies. But instead, all the planets and planetary systems out there, they're just so different than what we expected. It's partly because we don't have the technology yet to find a true Earth twin or a copy of our solar system. It's very hard to find. But it's actually easier to find planets closer to the star. And so this particular one, it's called Kepler 10b, and there's a whole bunch like it. It's a super-Earth, a more massive planet than Earth, so close to its star that its orbital period, its year, is less than 1 Earth day. And this planet is so hot, we would melt before we got there. But if we could get there, we would see this fiery inferno where the surface is so hot as heated by the star, it's hot enough to melt rock. And so there wouldn't be we're not imagining a planet with volcanoes spewing out lava, but actually just liquid lava lakes, because they're so hot, 2,000 Kelvin, that the rocks are all melting. So when I was 16 years old, I actually found out, I lived in a city, I grew up in Toronto, Canada, and I went to my local university's open house. And there I went in, and I actually found that you could be an astronomer for a job. I was so excited. I think it's one of the top 10 days of my life. And I rushed home and I told my dad, he's not alive now, but I went home and told him, and I got a long, furious lecture. He just looked at me and he went on, and he just went, Sarah, you have to be able to get a job and support yourself and not rely on any man. That was actually great advice. But I want you to know that I was really surprised by that reaction. It hadn't occurred to me because even though my grandparents, immigrated to this country, to Canada, it didn't occur to me that I actually had to go out and get a job and be able to support myself. So that actually gave me something to think about. So when I went to university, I definitely took all the sciences. I took math, and I ended up here, and I'll come come back to that in a little bit. But I did always love astronomy. And one thing I learned along the way, which is why I'm telling you this story, is it's really important to find something that you love doing that you're also really good at. And I know there's a lot of different careers out there in math, so the dads in the room, you don't have to worry. You're usually always employable if you have a degree in applied science. And so you don't have to worry about that too much. Now, what I'm going to talk about next is how we found most of the planets I talked about. Now, most of them have been found by a telescope called the Kepler Space Telescope. It was a telescope, it's very different from Hubble, but it's built specially to look for planets. And here's like a picture of it. It's hard to see, but the people are this big right here. This is Kepler in the clean room while it was being built. It looks at a part of the sky that's so big. It's a moon would fit in the little corner here. It's a huge patch of sky, and Kepler looked at one patch of sky for 4 years. And what Kepler did was it measured the brightness of stars as a function of time. Now here, I want you to look at this. There's two things going on. Can you see the little dot going in front of the star? We don't spatially resolve any stars like that other than our sun, but this is an Earth-sized planet transiting, going in front of a sun-sized star. Now look down here. This would show you the measurement Kepler's doing. It's measuring the brightness of the star as a function of time, and the planet goes in front of the star and it drops by a tiny, tiny amount. And I'm going to play that for you one more time, just so you can watch the curve at the bottom. Imagine that. Kepler looked at hundreds of thousands of stars, taking a data point every 6 seconds, then binning it on board and downlinking it to Earth. And we had the final light curves have intervals of 1 minute or 30 minutes. Look, imagine just looking at that, taking all that data, and it's pretty messy to begin with. It has to be kind of cleaned up and getting very precise photometry, we call it. That's actually what Kepler did. I had some real data to show you, but I realize I probably don't have time to dwell on it at the moment. But let's just say, look, here's the brightness of a star as a function of time. And this is hundreds of days. And here, it's hard to see the transit, but this little arrow is pointing to it. And you can see there's times when the spacecraft wasn't working because it had a problem, and it goes into safe mode until the engineers here on Earth can send it a computer command and wake it up. And other things happen. But this is raw data. This is processed data. But at the end of the day, there's so many planets have been found this way, thousands and thousands of planets. Now, what I wanted to tell you about this is, if you had time, I know you're on a little break here before the announcement of the winners, but I wanted to tell you that actually this problem is accessible to you. If you wanted to write out the equations that describe this light curve as the planet goes in front of the star, you actually could do that. And in fact, in colleges, I bet even some high schools, but colleges all around this country, people even take data as a student of a star with a transit, usually a giant planet transiting, and you can actually write down the equations and write a computer code, and then you yourself could extract how big the planet is, how far it is from the star based on its period and the mass of the star and things like that. Well, I wrote down the one equation that would be so simple for you to just see, but when the planet is totally coincident with the star, when the planet's totally in front of the star, that depth, the drop in brightness, the actual brightness would be 1, I've normalized it to 1, minus essentially it's the area of the planet to the area of the star. I just wrote pi r squared planet over pi r squared star, and you could write that down. Now the ones at the edge are a little more complicated when that planet actually is going in front of the star. I didn't have time to write it out, but I wanted you to know that it's the curvature of the planet and star as well as the transit being off center that makes the math problem more challenging. But it involves geometry, trigonometry, and not even really calculus, but just, finding out the area of something, so you probably need a bit of calculus to solve that problem. Now, actually, I want to tell you about one of my biggest discoveries that involve math, and you don't have to read through this, but I wanted you to be able to glance at the equations and just see that it's math that would be accessible to you even at your level now. And in this one, at the time I had my best friend. It was the first time in my life I had a best friend in math, but I was like about 28 years old. Finally, I'd met another person who liked math. Her name was Gabriella, and she really was great in math. She should have been a mathematician, not an astronomer. In her case, ironically, her dad wanted her to be an astronomer because he never got to be one, and she ended up eventually leaving astronomy and going to do something else. But what we did was we wrote down the equations that describe that light curve, and for the first time, we said in a special case, when a planet has a circular orbit, there's a unique solution to the equations that describe the light curve. Now, I'm guessing, I haven't seen the test you took this morning, but I'm guessing at least one of the equations had more than one solution, because they always seem to. In this case, we just lucked out, and there was a unique solution. And one night, we were working really late till like midnight, and around just before midnight, we were working so hard through the equations, and we looked at each other, and we both burst out laughing hysterically, because we discovered that from that light curve alone, we could actually tell the density of the star. Now that isn't so meaningful for you personally, but it was this crazy thing. From a light curve of a planet going in front of a star, how could you tell the density of the star? Just for people in physics, I'll mention it, but when the planet goes in front of the star, the time that it takes to cross the star compared to its whole orbit, that helps to tell you the size of the star in relative proportions. And Kepler's law ends up giving you, in relative proportions, the mass interior to the orbit. And you end up being able to cancel things out and end up with the density. Now, this turned out to be super impactful because when we're looking for planets by the transit method, did I show you this light curve here? Well, how do you know that's a planet? I mean, you don't know because you haven't studied this yet, but it turns out it's very hard. If you got this light curve, if you measure the data and fit this, there's about 10,000 more hours of work to find out if it's a planet or not. And that is done by astronomers using different techniques to make sure there aren't stars in the field that are mimicking a planet and other things. But if you get a good light curve and you get the stellar density from the light curve and compare that to another method, just taking a spectrum of a star to get a density, you can actually right away tell whether it's a good planet candidate or not. So that was one of my biggest discoveries, was using math. And I still love transiting planets. I work on other things now. But I wanted to tell you that I came to MIT about 10 years ago, and MIT is such a great place. When you come here and tell people about your ideas, I'd never heard anyone say, well, except maybe once, that's a dumb idea, don't do that. Instead, you have a crazy idea, and people say, wow, great idea, I believe in you. And so actually, when I first got the job offer at MIT, I wasn't sure if I should take it because I was just worried it would be way too much work. I had a job already, and it didn't involve teaching, and it didn't involve all the committees that we're always on, and all those other millions of things. And so at that time, my dad, I told him about the job, and he's like, you should take this job. It's so great. It's an opportunity. Always take a great opportunity. And then I was really surprised by his reaction because after I agreed with him, okay, you're right. I don't know if your dad's always right, but like, okay, you're right. I should definitely go there. Obviously, it's such a great job. He was telling me it's a no-brainer. I'm like, this is good. I think I'm proud of myself. I'm 35. At the time, I was 35. I'm like, I'm going to MIT. I have tenure. This is like the best I can do. It's like, that doesn't usually happen always at that young age. Well, it's young relative to my age now. And he looks at me and he's like, Sarah, you know what? Here's the thing. I'm sure there's a better job out there. And I know you'll get it one day. And I don't want you to be limited by your own internal thinking. And I was just like, wow, I mean, really, he was telling me to take the job, and he was so excited, and then he told me not to be limited to what I'm thinking. And so although he's no longer alive, I always carry that with me. And actually, then I'm not limited at all in my thinking, and that leads me to the next part of my talk. And here, I just first had to tell you that transits are only the first part of a long story, because when that planet goes in front of the star, the whole system has to be lined up just so. But actually, planets come in all orbits. It's just random the way that the star and planet system is born. We don't know that, and we actually need a whole new technique to find planets. And this one is called direct imaging. We want to be able to block out the starlight so that we can see the planet itself, the planets themselves, actually. We want to be able to block out that starlight. And the challenge here is that our own Earth and Sun, if we imagine them, looking at them from far away, guess what? Our Earth and reflected light is 10 billion times fainter than our sun. And so we actually have to find a way to block out the starlight to 1 part in 10 billion. And that's a huge number. I think that even if I know you're all math here, but if you like physics or engineering, you've never measured, I could ask, has anyone here ever had to measure anything to 10 decimal places? Because that's what we're talking about here, measuring and canceling out. And so I wasn't supposed to be limited by my own internal thinking, so I'm thinking it's possible. And so I and a lot of other people, this concept I'm going to tell you about next, we call it the star shade. And what it is it's a giant screen that's going to be put in space, a screen that's tens of meters in diameter. And here I'm to explain one final point to you, and that is if we put up a big circular screen in space, do you know what would happen? If we were to put a big circular screen up, formation flying very far from the telescope, it's like trying to block out one of those lights with your hand far away. If we put up a circular screen and we get to block out a point source, a star, we wouldn't block out that light, actually. What would happen is light acts like a wave, and it would diffract around the edges of the big screen. And this is like analogous to dropping a pebble in a pond. You'll see ripples. And that first ripple in the pond, from light acting like a wave, it's way brighter than the planet you're looking for. So that big circular screen in space will never work. And if you can see it, you're supposed to be able to see the light ripples here, which is an airy ring pattern that you get from here. If you can't see it, don't worry, you'll come across it sometime, either in high school or college. So what shape should we use? It turns out there's a very special shape. If you can put a shape up like a star, that's why this is star-shaped, you would actually get an image like this. And this would be like dropping a pebble in a pond. And all of a sudden, that area all around the pond is perfectly smooth to 1 part in 10 billion. And all the waves are pushed out to the edges, where it's crazy wavy all at the edges. And that's actually the concept of the star shade. And I wanted you to know that the optimum shape of the star shade actually comes from applied physics and math. And here's an equation. I'm not expecting you to recognize it. This is a Bessel function. But actually, a lot of math goes into the physics of diffraction, how light acts like a wave and bends around objects. And physics and applied math were used to find the optimal shape. So here's a little more about the star shade. We could imagine a star shade and telescope launching together, and they would separate in space, and the star shade petals would unfurl from a stowed position. And this inner truss would expand with those petals snapping into place. Now, this thing has to be made very precisely in order to reach that 1 part in 10 billion starlight suppression. So those petals have to be made to within 150 microns. The petals have to deploy to within millimeters of each other in a special position. And that star shade would have to fly tens of thousands of kilometers from the telescope. And they'd have to line up very precisely. Although they have hundreds of kilometers in this direction, in this lateral direction, it's only meters. And that formation flying problem at tens of thousands of kilometers is a huge challenge. And that's the one that engineers in this country are working hard on to actually figure out how to solve that problem. Many of them are out at JPL or Northrop Grumman. And I led this project for a couple of years. Now here is, just so you know it's real, it's really going on, here is a video taken a couple of years ago of the star shade. See the petals? They're unfurling from their stowed position. And that central truss, by the way, was not made for the star shade. It's left over from large radio deployables in space. So we have sent very large things to space before. They just didn't have those petals hanging off the edges. Now here, there's only 4 petals because it's all that we could afford to test at that time. Now here's the second part of the star shade deployment. I always get asked, why are there people in this movie? The people actually are, it's not that to show that this deploys automatically, but that the petals reach the same position relative to each other over and over and over again for 25 times that this thing was unfolded. It's a time lapse because otherwise it would be too slow. So there's the star shade. And out here, I have one more picture of myself and 2 of the other people on the team, Maggie Turnbull and Aki Roberge. And look at this star shade petal. That's just one petal. Look how long the tip is. It looks dangerous. It kind of is. It's all built out of very lightweight material. And this picture was taken out at JPL. So at the end of the day, in the future, when the star shade flies, it will be at least a decade from now. It takes a long time to develop something that new and that complex. And going to space is even harder because we can never go up there. Except for Hubble, we can't go there and fix anything. But you just pay attention, and in the future, someone will be presenting an image like this. This actually is a real photograph. It's a real image taken by the Voyager 1 spacecraft at 4 billion miles away. And this, I hope you can see Earth here. It's just one little pale blue dot. And it's stuck in this big pink glow. This pink glow is scattered light in the camera optics. We think our real image of Earth, another Earth, in the future will look like this because we have a zodiacal dust. We actually have a problem with our asteroid belt. The asteroids bump into each other and they generate dust. And that dust ends up looking very red. It's scattered at red wavelengths. So that's what we're going to look for. And that's the real way that I believe we'll find Earth 2.0 is with the star shade. There are other ways to block out starlight, but for many reasons, I believe the star shade is the best way to go right now. Okay, so now I'm going to summarize. Exoplanets are planets that orbit stars other than the sun. We know of thousands of exoplanets, and small rocky planets are common. I actually showed you a few pictures. They're not real images, but just speculations of what we think those planets might be like. Transits is the main way today for finding small exoplanets, and I hope if there's one thing you can walk away with, it's that the transits, the light curve, and that's how we found most of the thousands of planets that we know about today. The search for Earth 2.0 requires new space telescopes. We have to get above the blurring effects of Earth. And I just wanted to end by saying, space is big out there. It's really almost limitless. And I just hope after today, you all came out here and did the test, and I'm sure that a lot of preparation went up to this time, that there's so many opportunities out there, and this is really just your first step in what I hope is a really exciting journey for you. Thank you. And we have time. I know we have time for a few questions. I'm going to leave this up for you to read. And if you have a question, please raise your hand, and I'll take it. Oh, question? Let's see. Yes.
So this is far further out in the future, but once we find Earth 2.0,
the question is, once we find an Earth 2.0, what are our next steps? And this is the good part where I can turn that back to all of you, because you'll be the ones who are figuring that out, you and your generation. And actually, there's a number of things that could happen. The first thing is we want to know more about the planet. And so it's sort of a greedy thing in astronomy. We always want to launch the next space telescope, a better one, and look more closely at the planet. So I think the first thing we'll do is that. Secondly, SETI, Search for Extraterrestrial Intelligence. They're focused on that planet and listen to it. We're kind of thinking whether we should be, I think you or whoever is in charge will be thinking of should we send them a message, see if there's intelligent life on that planet or not. That's a bit contentious right now. But I think the most exciting thing that this will galvanize is how to go to another star system. Right now it's out of reach for us because we don't know how to travel fast, but there are people all around actually working. It's sort of like the dirty little secret people don't like to talk about, but people really take it seriously. How can they have advanced propulsion and go fast enough to travel to another world? Because from here, we're pretty much stuck with that little pale blue dot. We don't really have a way. We can use all our special tools and telescopes and remote sensing, but I think that at the end of the day, we have to find a way to get there. Yes, back there.
Now I want to see the I have a question. When you have a star shape, which direction you have, how do you determine which direction to point?
Good question. When you have the star shade, how do we determine which direction to point? Now, one thing I didn't mention was the star shade has to line up to a star of interest with the telescope. And then when it's finished with that observation, the star shade or the telescope has to move across the sky to the next target. So believe it or not, on our team, we actually had one person working full time to figure out which stars to look at, which direction to point, how to line up. But the bigger picture is that the sun has to be out of the way, the moon and other planets like Venus, they're bright, they're a problem. But really, we have our top list of stars, just like you have your favorite books of all time or your favorite movies of all time. We actually have our list of about 100 stars, the best ones for the search. And we try to make sure that the star shade moves optimally so it's not moving too far. We don't want it zooming across the sky and then zooming back. And so the answer is, with a lot of careful thought, we figure out which star to look at and where to point and how to move it. Yes, right there.
So you mentioned that you have to move the star shade with the telescope, so you're looking at different stars. Is the star shade powered by itself?
The question is, how is the star shade powered if it has to move around? Well, it actually has a whole spacecraft attached to it, and that's a flaw in the video. It should really show there's a spacecraft with big fuel tanks. And so the star shade has fuel, and that burns that fuel to move around. But actually, the future of space is really tremendous. We imagine in the future that the star shade material itself, there might be a way to even embed solar panels on the backside of that. And there may be some way that it can have a longer lasting fuel with solar electric power and move that way. But it has to have some way of getting fuel on its own. Okay, well, I think that we're done with this, and we can move on to our announcement of the winners. Thanks, everybody.